Welcome back to a new video about controller design using the frequency response method. This is our example number 7. In this example, we will look at the lag lead controller design using this frequency response method. Of course, we will work out the calculations step by step and also verify these in MATLAB simulations. So let's look at our example. We have the following feedback system. We see the lag lead controller here in cascade with our plant G, which is shown here, which is a third order system. We want to design this lag lead controller such that the lag lead controlled system has a velocity error of 1 over 12 for a unit ramp input, and it must be has an overshoot of which is maximum 13.5%. Okay, so these are the specifications for this design. And the lag lead controller can be given in this configuration, this transfer function. You see the KC, which is the proportional controller part. This is the lead part. You see the Z lead and a P lead, and this is the lag part. So we see 3 parts together that are multiplied, and we will also calculate them separately. So looking at solutions, we start with first the damping ratio required for our overshoot. We see the MP of 13.5%, which is the scalar 0.135. And then you substitute the values in this format, in this formula, we get 0.538. Now we need to calculate the required phase margin for our final design. Now let's do that in this formula again. We saw that also in the previous videos. The damping ratio is now calculated. Now you can use this formula, and when you do that, you get 55 degrees approximately. So we need to make this in the final design. But we know the lag lead controller will increase the phase margin frequency. That is because of the lead controller. And the phase margin will then decrease because of that increase in the phase margin frequency. So to compensate for this phase reduction, you can add some extra phase to the required phase margin. So it can be between 5 or 10 degrees, or maybe smaller, maybe larger, depending on the specification or also the requirements. So in this case, we will add just 5 degrees extra, so 55 plus the 5 will be get 60 degrees, such that the lag lead control system will get at least this 55 degrees. Maybe we have put here too much, which is not necessarily that much, but that is just for safety. Okay, now moving on, and we start now with a P control system, and we see how much performance that can get in this configuration. That means the controller is just a K1, which is just an amplifier, just a gain. So we have now the loop transfer function, L1, called for this P control system, which is just K1 times the plant, which is shown here. Now let's now calculate the K1. Since there is a velocity error requirement of 1 over 12, we require the velocity error constant for this unit ramp input to be this. Because this is the formula for EV, which is the velocity error constant, is 1 over the kV for unit ramp input. This formula is only valid, by the way, when you have a unit gain feedback. Now when you calculate now the velocity error constant, which is kV, is 1 over the EV over, that will be then 1 over 12, which is exactly 12. So that means looking at the formula of the kV, which is then the limit as approaching 0 for s times the loop transfer function what we have here. Now when you do the calculation now, you get now K1 over 4, because this is s and s that will divide out. You get, when you substitute 0 here, you get 1 times 4 in the denominator, so you get K1 over 4. That must be equal to, together, 12. So that means K1 must be 48. This is now just a specification for our velocity error condition. But let's also calculate now the phase margin frequency and also the overshoot what we get from this P control system. The phase margin frequency, omega P M1. Okay, now we first transform this L1 to the J omega domain, which is shown here. So we replace the S by J omega, and we continue. We set this loop transfer function, the absolute value of that one, equal to 1, and then we solve it. So that's just magnitude equal to 1, and you get the 3.0102 radians per second. And that is now defined as omega P1, which is the phase margin frequency for this P control system. Let's now calculate the corresponding phase or argument for this P control system loop gain. Now that we look at the argument of L1 at that frequency of 3.02. Now when you look at the argument formula here, which is the argument of the numerator, which is 0, minus the arguments of the denominator, which is the minus, which is a pure imaginary value, which is just 90 degrees, and also arctangent formula here, etc. It's all given in the great detail, of course, in other videos, so I just go a little bit faster. And this must be then, when you calculate that, minus 199 degrees when you put this 3.02 in this formula. But that phase margin will now be, when you use this formula, will be minus 19 degrees. And we know we require at least 55 degrees to get this overshoot of 13.5% at max. Of course, we added also 5 degrees extra to get the 60 degrees, but definitely this 55 degrees is not even met by this P control system. So we can say P control system cannot provide this phase margin of 60 degrees, also not 55 degrees. So this design is only possible for just the velocity error specification, but not for the overshoot. So we need to move on. And by the way, it's also unstable. It is not even usable because the negative phase margin means that there is an unstable system. So forget the stable system at the edge, you need to have a phase margin of at least 0. Okay, that means we need to move on and look at the situation in more detail and also a little bit more complicated controller. So looking at the closed-loop system, it must be stable and also satisfy the given requirements. So it must be the following. The controller must now provide 60 degrees, we already need it, and then also compensate for this minus 90 degrees. That means we need to go up by 79 degrees, which is a lot. So lag lead controller must now increase the phase margin and thereby also decrease the overshoot to a maximum of 13.5%, and also the velocity error must stay still at 1/12 at max. So there are still some specifications we need to meet. Okay, we will now design the lead controller first and then the lag controller. We will do that separately. Instead of using separate lag controller and the lead controller, we can also take them as one and use just one parameter. This is just a method. It is not the only method. You can see also in other literature and books and also papers that they do it in a different form. This is in my opinion, the most convenient way to work out the lag lead controller. I start with the lead controller design and show you how the lag controller also done after this analysis. So lead controller parameter beta is now used, and that is given by this formula, which is then related to that phase margin we needed, which is then 79 degrees. That is how much phase margin we need to add to get this 60 degrees for our lag lead controller. And when you now do the calculations here, you get 0.0093, which is a very small value, almost 0.01. This is maybe possible, but not really practical in some component values. So you can say, let's now select the new phase margin frequency, which is smaller than this 3.02 radians per second, and that will make then also the realization of this controller also easy. So that is an option. So we can say, let's now make the phase margin frequency smaller by reducing the required phase contribution of this system. So phase of the loop transfer function of the P control can be increased from minus 199 to minus 180 degrees. Now, which will then increase the phase margin from minus 19 degrees to 0 degrees. Okay. Now this frequency can then be calculated using the argument of the L1, and that equates to minus 180 degrees, which is at the edge. That means we increase now the phase contribution of the original P control system by 90 degrees to get the 0 degrees. And remember, this was the L1 for our P control system. So we now calculate again, or express the argument formula here, and equate that to minus 180 degrees and solve this, you get exactly 2 radians per second. Now we can equate that as the new phase margin frequency. It could be the case that when we simulate this, the phase margin frequency we have now calculated could be a little bit smaller. So that is what we need to check also in the simulation. Now, setting this new phase margin frequency of 2 radians per second, and the loop transfer function with a p control will then provide 0 degrees. That is now the condition. Now we require a phase margin of 60 degrees max, because we need to now go from 0 degrees up to 60 degrees instead of from minus 90 degrees up to 60 degrees. So that is just an easy, more, let's say, less complicated design. Now we need to calculate a new beta parameter. Now the required value of the lead control parameter beta is now calculated using this 60 degrees instead of the 79. And that will be then 0.0718. It's much larger than the previous calculated beta, so this is also easier to realize. So we'll go for this beta. And we have also our new phase margin frequency, and we move on with our lead control design. Now we first determine the lead control 0 and the lead controller pole. Now they are related to a omega max, which is a frequency which will give you the maximum possible phase for this lead controller. And that is of course chosen as 2 radians per second. So we need to select that at that omega max. Omega max is related to the lead 0 and the lead pole by this expression, which is the geometric mean actually of this lead 0 and the lead pole. And they are related in this format. So the z lead is equal to omega max times the square root of beta. And the p lead is the omega max over the square root of beta. So when you multiply this together and take the square root, you get again the omega max, which is omega p m2. So when you calculate now using the beta, we have calculated also the omega max, which is set to omega p m2, you get this, and you get for the p lead this one. When you do the calculations here, you get these two values for the z lead and the p lead. Now taking these together, you have now our G lead, which is now the lead controller transfer function, of course without the gain we require for our velocity error. That is just a separate calculation we have done already for the P controller. Now when you now substitute value for the Z lead and the P lead, now we have our transfer function already required. So we have now the KC, which is 48 already calculated, and we have also this part, so now the final part, which is the lag controller. Now going to the lag controller, it's also related to that beta. So the lag controller 0 and also the lag controller pole must be determined. Now to reduce the effect of the negative phase contribution by the lag controller at the phase margin frequency, it is important that you select a specific 0 location for your lag controller. So for that, we set the higher break frequency, the lag 0, about 1 decade below the phase margin frequency. This is just a rule of thumb. You can also take it a little bit smaller than that one, or maybe a little bit larger if you prefer that, and also it is best for your design, but most of the time it will be 1 decade below. That means we have omega p m2 as 2 radians per second, so the z lag will be then 2 over 10, which is 1 decade lower, 0.2. And the p lag, which is the lag controller pole, will be then the beta times that z lag, which we just calculated, that will be then 0.0144. Now taking this together, now we have our g lag transfer function specifically, and when you now substitute the values, you get now here the g lag transfer function. Now taking these together, we have the kc, which is 48, g lead transfer function shown here, and g lag. Now we can now multiply that together. We have our transfer function for the lag lead controller. So the lag lead controller transfer function includes the required proportional gain K1, which is 48 for the velocity error specification. And now the multiplication of the 3 parts, you will get this transfer function. And when you a little bit combine them together in one fraction here, you get this transfer function. Okay, moving on, now looking at the loop transfer function for this lag lead controlled system, let's also check that the velocity error is indeed 1 over 12. Now, the lag lead control system has the loop transfer function of L2, which is shown here. So the plant times the controller. It's shown here, and when you combine them together, you will get this L2. Now, for the velocity error calculations EV, we need to calculate again the velocity error constant, which is KV. And now for this L2. When you now substitute the value or the expression for the L2 here, and also divide out this S first, and now equate now the S to 0, or approach that to 0, you will get 48 times 0.2 times 0.536, which is shown here in the numerator, and then 1 times 4 times 0.0144 times 7.464. That's all shown here, and that will give you approximately 11.97. Remember, we had for the KV in the P controller design, 12 exactly. So this is approximately 12, but a little bit smaller. So you can say, let's increase the gain or adjust the controller parameters such that this is exactly 12. But it is close, so I can say it is approximately 12. And so our EV, which is 1 over the KV, is indeed exactly now in this case, but that is very close to 1 over 12. So we can say this is fine and it will do the job. So the velocity error specification is definitely met with this lag lead controlled system. Okay, now moving on and now looking at the simulation results. First we start with the P controller, which is a gain of 48. I just want to show that this system is indeed not stable. It's shown here. So the closed system is not stable. You can see also here that this is the loop transfer function with a 48 as the gain, K1. And you see here in this label that the phase margin is minus 18.7. We had calculated minus 19, so very close. And we also see the phase margin frequency of 3.02 radians per second also we have calculated. So moving on to the next step, which is then the lag lead controlled system, which is shown here. And this is a transfer function. And that is now also again the loop gain Bode plot for this system. Now loop transfer with the lag lead controller. You see again the loop transfer function here, L2, and this is the label where we are interested in. And this, you see here, the 69.1 degrees, which is a lot larger than the 55 degrees. So we see a lot of headroom here. We also see the 1.31 degree radians per second, I must say, instead of 2 radians per second. So you see that it is much smaller compared to what we have as the phase margin frequency. And also our phase margin is much larger than the 55 degrees we had anticipated. So that is not bad, it is actually much better. So we see that this loop transfer function will do a better job than we have estimated. So that's good. And if you look at the 2 radians per second here, we see the phase is minus 125 as a degree. So you see also that this is also some a little bit smaller. But this is just an estimation we of course made, so you see that it is now in this case in our favor, so that's not a problem. So we met our minimum required phase margin for our overshoot. But of course let's look at the overshoot. Is that really much lower than 30.5%? Now you see here the closed transfer function T2. This is the unit step response for the lag lead control system. And you see here the overshoot, which is 7.4% approximately, which is much larger than 30.5%. So we see the system is definitely doing much better. And these are the summary of the results. You see the final value is 1. In this case, steady state error is 0 for unit step input. Okay, moving on to the ramp response. Now you see the blue line is the unit ramp input, which is a linearly increasing line, which has a slope of 1. You see at 10 seconds it has a value of 10. You see also some labels here, because again this is the closed transfer function for the lag lead control system. You see at time 10 for the response is 9.71, but of course this difference is still larger than the 1 over 12. So you need to look at actually some time later. So in this case I look at 20 seconds. And I see now at 20 seconds is 19.9, but you still see that the error is here 0.1. That is just due to this rounding of error in the label. So if you make this, let's say the expression here more accurate, you can get that exactly at 1 over 12 if you want. So you can also look at larger values for the time. I checked that really because if I want to do that, the picture will be a little bit small, so you cannot read it carefully in the video. So I really checked that, and this is definitely 1 over 12. So this system is really doing what is required. So we also see in the unit ramp response that the required velocity error of exactly or at least 1 over 12 is definitely the case, and also the overview we have seen that's also met. So we see that our design is completed and also according to the required specifications for this example. Alright, this is our example about the lag lead controller design using the frequency response method. We have seen how we can determine the required gain for our proportional controller, and then the lead controller and then the lag controller. Together we combine that to the lag lead controller. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.